I did mine in 30 minutes, but I didn't know it was like McDonald's for it, so one of them turned it in. So,
When I spent 28 minutes on one of those papers, got a 70.
and it was
Spent
bad.
3
Like,
days.
Okay, we're going to continue on today. 21 is what we're going to talk about today. As we begin, though, I want to talk about what did we learn yesterday? Somebody tell me something about yesterday. Critical points. That was a word we learned yesterday.
Well, it can be an open interval or closed interval, right?
All right, so let's talk about what critical points are first, though. What do we mean when we say a point is a critical point?
No, critical point is when the derivative is extreme.
Derivative is 0, or no, endpoints are not critical points. That's something else that you're tying in there. But there's another way it can be a critical point. It's what everybody always forgets. Derivative is 0, or, thank you, Sally, f prime is undefined. Okay? Now, that's what critical points are. So we find critical points by setting the derivative equal to 0 or figuring out where it's undefined. Now, what's another word maybe that y'all remember from yesterday? You were talking about it, maxes and mins. What do we call them kind of as one thing? Extremes, okay? Extremes are, I think the plural of that could be seen as extrema or extreme. Remember, we call these global or absolute extremes. And we're really just talking about where maxes and mins occur, okay? Does everything have a max? Does everything have a min? When can it not have a max or will not have a min? Whole. Okay, so what's a calculus-y word that says something has a whole? It's what? The whole is removable, but what does it mean though? Continuous, okay? So to be extremes, to have extremes, it has to be, well, I won't say that, to have extremes. One thing that we're looking for is continuous. If something's continuous, does it have to have extremes? Yes, it does. Has to have a max and min if it's continuous. Is that continuous? Does it have a max and min?
No.
All right. Nope. So to guarantee that we have extremes, it has to be continuous and what else?
So you can't call a max and min infinity?
Max and min's a point. Yeah. So there's one other thing that has to be true to be guaranteed. We've got to have a max. That we've got a max and a min. Continuous and something. Yes, closed interval. Closed interval. Okay. So we talked about yesterday. If we have closed. If we have these two things, if it's continuous, if it's a closed interval, then it must have a max and min. All right? Must have a max and min. Okay? Y'all comfortable with that? All right. Where do extremes occur? Because right now, we know that extremes occur. We know that if it's a closed interval, it has to have them, but where do extremes occur? We found certain points that we could test. Obviously, we couldn't test every single point because we'd be there forever. But where do extremes occur? There are two different kind of points. Endpoints or critical points, okay? Okay, so that's what we talked about yesterday. Does anybody remember the one thing I said yesterday that was very important? I said, you're going to use this all year long. If you don't have any idea what to do this.
Isn't it find when f prime equals 0?
Find the derivative, set it equal to 0. That's the right thing to do about half the time, even if you don't know what to do. So that's a good starting point for you, okay? So now today we're going to take a different road, talk about two other theorems that may seem unrelated, but then next week we're going to tie them all together, okay? And we're going to start off in the courtroom today, okay? So who's going to be the lawyer out of this group? Mr. Butt's the lawyer. Okay, so here's, Mr. Butt, your client was driving on 316, okay? And one GSP officer, bing, pegged him at 55 miles an hour. Another GSP officer, 5 miles down the road, 4 minutes later, bing, 50 miles an hour. And he gave him a ticket. Is there enough evidence to convict him? He drove down the road. First officer said he's going 55. 4 minutes later, second officer said he's going 50. And boom, they hit him with a ticket. How do you defend that? Is it defendable? Always defendable. Okay. So what do y'all think as a class maybe? Is there enough evidence to convict this guy of speeding? I mean, he was going 55 one time, he's going 50 the other. Is there enough evidence written on the board to convict this guy of speeding? Yes? How do you figure?
If he went 5 miles or 4 minutes, so he had to be going faster.
5 miles over 4 minutes. Well, we usually don't measure time usually don't measure speed in minutes. So 4 minutes is what? 5 miles over 4/60 of an hour. That works out, what, 75 miles an hour? I think that's right. 4 going to 61. Yeah, 75 miles an hour. So his average speed was 75 miles an hour. Would y'all agree mathematically with that now? I mean, he drove 5 miles. It took him 4 minutes to do it, so his average speed was 75 miles an hour. So he can give him a ticket? What do you think? I mean, yeah, there's enough evidence there to give the man a ticket. Because if he drove from here to here, a set distance and a set amount of time, he had to be going 75 one time, didn't he? Probably had to be going higher than 75 sometime, didn't he? So we can give him a ticket, all right? There's a lot of calculus proving that he can do, showing that, okay? And that's kind of what we're talking about today. The two theorems we're going to be talking about today are theorems that play into this exactly, okay? So let's start off by talking about, well, you know what it means to be continuous on an interval. We did that yesterday. Continuous means it's nice, and once I start drawing it, it's going. It could have a sharp turn somewhere. It could go abruptly, but it's moving all the time. There's no holes, there's no jumps. We're going to talk about two theorems. The first one that we're going to talk about is Rolle's theorem, and we want to break it down for you. These are things that you've got to commit to memory, okay? These are things that there will be questions on the exam referring to Rolle's and MVT. You're going to have to say, is it Rolle's or is it MVT, or by Rolle's theorem we can show this. So let's break this down. If F is continuous on close bracket A, comma B, close bracket. Okay? We know what continuous means. What's the significance of the square brackets around A and B? The points are included. So if F is continuous all the way from A to B, okay? So we're going to start here at A. let's put an X, Y axis here. We're going to start here at A. We're going to end here at B. Okay? If F is continuous from A to B and differentiable on the open bracket A to B, on a parenthesis, what does it mean that it's differentiable? How is that different than continuous? It's one big difference looking at it. Yeah, F prime. If F prime is continuous, yes. How do we know looking at it that it's differentiable or not differentiable? What if it's not differentiable? It has something in it. Does anybody remember? Right. That's the key, okay? Sharp turns. Okay, so look at what we're saying. F is continuous from A to B. It's differentiable on A and B from A to B. It might not be differentiable at A. It might not be differentiable at B. It's differentiable. That means we can find the derivative. There's no sharp turns. And F of A equals F of B. What does that mean? F. They're both the same. That's right. The Y. So we start here and we end here. Okay? There's 7 of you in here. I want all 7 of you, not at once, to come and draw a function, different functions, that meet those criteria, that start at A, that end at B, that are continuous, and that are differentiable from A to B. So, somebody be bold and brave and walk up there and draw one for me. Don't be shy. Don't know what it looks like. There's an easy one all of you could draw. That would be, you could do that and get me off your back. Make it harder for everybody else. Continuous. So it's got to be nice and continuous. Be the man now. Go ahead. You can do it. I'm confident in your abilities. Continuous and differentiable. So it's just got to go and it can't have any sharp turns. Wow. He picked the easy one, made it hard for the rest of you. Okay? It's continuous. It doesn't have any sharp turns. That's good. Oh, look at there. Starts, it stops. Ooh. Got some brave people now. Come on now. Very good. Very good. Excellent. Look at there. People, y'all can go home and say you drew in calculus class today. How about that? Good. Look at there. Wow. Very good. And there's a million more that we could draw. But all of those are continuous. Thank you all very much. I wanted to see if y'all were really alive this afternoon or not, okay? There's a million more we could draw. But all of those meet this criteria. Well, what does this theorem say? Then there exists at least one number, C, between A and B. So that's saying for every one of these functions, there's at least one number between here and here, such that what's true? Maybe hard to see. F prime is 0. Now, what does it look like if F prime is 0?
It's a
horizontal tangent line. So, let's look at some of these. Let's try to look maybe at the red line to begin with. The red line is horizontal, isn't it? So, the derivative is always 0 for it. So, would all of you agree it's easy to see there's the derivative 0 there, okay? What about this blue sine-looking wave in here? Do you see? How many places do you see? It's hard to see in here. On this blue sine wave right here where the derivative is 0. 4, maybe 5, depending upon what's happening here. Right there, right there, right there, right there, right right there. What about this big green arch here? How many places? One up here. And if you look at all the others, you see there has to be a place where the derivative equals 0. Okay? Does that make sense to you now? All right? Let's think about it. So that's just another theorem that's existence theorem. We've got several theorems that we've said existence. Does anybody remember what I said it means that it's an existence theorem? What do you think it means, existence? All it tells you is that something exists. What does it tell us exists? There's a number, there's at least a number between A and B so that the derivative is 0. Does it tell us how to find that number? Does it tell us how many of those numbers it is? So there's got to be at least one. There could be 1, there could be 2, there could be 20, there could be infinitely many in the case of the red line here. Okay? So that's all Rolle's theorem says. But think about what that says for us. Okay? That tells us that if we can find a place on a function where these two places are equal to each other, what has to happen somewhere between there if it's a continuous differentiable function? Somewhere the function's got to go up and down, or down and up. Somewhere the function, in non-math terms, somewhere the function's got to turn to get back there. Does that make sense? Can anybody see where we're heading maybe with this? If we know that the function is 7 here and it's 7 here, what can you tell me about between 7? There has to be tell me something that you see happening there. There has to be a max or min. So suddenly, if we know something's continuous, we've got it, and we can find two places where it's equal. Well, boom, there's got to be a max or min in there somewhere. Okay, that's a good information for us to be able to have. That's how we're going to tie this with what we talked about yesterday. Okay, that's what Rolle's theorem says. And well, I'll tell you how I remember it in just a second. Now, I want you to keep Rolle's theorem on your device, and I'm going to put the next one up here, MVT. First thing I want us to figure out is what's different between Rolle's and MVT. Because when you start reading, you think, wow, this says the same thing. That's right. Here's the only difference between these two, okay? The only difference between those is that. So these are hard theorems to keep separate in your mind. Which one's what? Okay. Here's what I do. Here's how I remember. Rolle's theorem, the derivative is 0 and Rolle's has a 0 in it. If you're going to roll something down the road, it's going to go like this. So that means it's got a 0 in it. Mean value theorem doesn't have an O in mean value. Doesn't have an O in mean value, so it's not rolling, so it doesn't have a 0 in it. The endpoints are not equal to each other. Okay? 0 means the derivative is equal. Here, the derivative is not equal to 0. Okay? So let's see if we can get a picture of what this says. Mean value, F's continuous, F's differentiable. That's the same as we had before. But now the endpoints are not at the same height. They don't have the same Y value. Okay? Boom. Boom. Now, I'm going to draw just a couple of examples up here so we'll have something to discuss maybe. There's one. Let's draw this here, okay? So now, what does it say? If these conditions are true, then there exists at least one C such that this is true. Oh my goodness. What on earth is that saying? F prime of C equals F of B minus F of A over B minus A. Have you ever seen such an animal in your life? Slow. this hopefully reminds you of y2 minus y1 over x2 minus x1, something called rise over run, something called slope. Okay, so what is that saying? Saying if I can figure out the slope between these two endpoints right there, whatever that slope is, there has to be at least one point such that the slope is the same as that. Well, what does it mean if two lines have the same slope? They are parallel. Very good. So there has to be a place on this curve right here where the slope is parallel to that. Okay? Somewhere right along in there. On this green one, there's a place right along in there, right along in there. No matter what function I decide to draw, there has to be at least one in there. I mean, if I draw something like that, there's 1, there's 2, there's 3. But there's always going to be at least one. This is called the mean value theorem. So the only difference between them, both of them are continuous, both of them are differentiable. Difference is, are the endpoints the same or are they different? If they're the same, it has to be 0. If they're different, it has to be the slope. Really, couldn't you say this applies all the time? I mean, isn't this true even if f of b equals f of a? What if f of b and f of a are the same number? Then it's just 0, which makes it back to being Rolle's theorem, right? So really, if you were to take this part out right here, you could get by with just one theorem that says both things. Rolle's, there's got to be a place where it's 0. Mean value, there's got to be a place where it's the same slope as that. Okay? Now, what on earth is this thing over here? Can anybody tell me where I pulled that thing out of the air? How did I get f of b equals f of a plus b minus a f prime of c?
I mean, just by multiplying, literally just by, working the problem out.
Yes. Look at, let's go to a new page. This is the conclusion of Rolle's. F prime of c is the function value at b minus the function value at a over b minus a. Okay? If we wanted to simplify that, we don't like fractions. What if we multiply both sides by b minus a? Then what do we have? b minus a times f prime of c equals, over here we can cancel the b minus a's, f of b minus f of a. Right? Well, if we wanted to get f of b by itself, we could write it like this. F of b equals f prime of c times b minus a plus f of a. And that's the same thing I've got written on the other side, just a little different, looks a little different there. Either one of those, does this thing right here, especially, does that look like anything else we've seen before? Does that remind you of anything that we've been using quite a bit all year long? Yes. So y'all see the resemblance between them now? Y minus y1 equals m times x minus x1. So do you see that the point slope formula is kind of like the results of mean value theorem there? Okay, just trying to loosely tie some things together. They're going to get tighter over the next few weeks, okay? So let's see. Well, we've talked about roles. We've talked about mean value. What on earth does this really mean for us? How does this help us? So let's look at a couple of problems so you can see how you're going to start using this. Find the x-intercepts of the following function and show that the derivative equals 0 at some point between them. Okay? So, find the x-intercept. What does that mean? Yeah. Find the x-intercepts. Says we're going to set this thing equal to 0. X squared minus 6x plus 8. Find the x-intercepts, okay? I'm not going to help you with that for a minute. Let you get there on your own. Those of you that subtracted 8 from both sides and then factored out an x, just kind of quietly without making any fuss, erase what you did and start over. So the x-intercepts are what? Right. The x-intercepts are going to be 2, 0 and 4, 0. All right. So we found the x-intercepts. Now, how are we going to show that the derivative equals 0 at some point between them? How are we going to show something? Okay, if we set the derivative equal to 0, what is the derivative of this puppy? Thank you, 2x minus 6. So if we set that equal to 0, all right, so we know that the derivative is 0 at 3, f prime at x equals 3. All right, but now here's what I'm asking you. How do we show that? Is what we've done enough? And the answer is no. So how do we show that? We need to tie this to a theorem or something. How do we know that what we just did is the right stuff to do? Which of the two theorems that we talked about today can prove that this has to be true? Roles or mean value? Roles. Why roles? That's right. Okay, so how are we going to show that? This is kind of like you can think of this as a recipe. How am I going to do this? Okay? Since. What has to be true for us to use Rolle's theorem? Continuous, all right? Is f continuous from 2 to 4? How do we know? Now we aren't asking you to show that it's continuous from 2 to 4 because we can't do that. Do we know that this function is continuous from 2 to 4? You should know that by now. How do we know when a function is continuous? By looking at it. Or better question, easier question. What do we look for a function to not be continuous? Fractions, specials, logarithms would be kind of special functions. One other that we talked about. Two others actually. Piecewise and square roots. Okay? Do we have any of those in this case? Okay, so it's going to be continuous. Okay? Since f is continuous, from A to B. What else has to be true? F's continuous, and what? F of A equals B. Instead of A to B, let's write the actual numbers there, 2 to 4. And f of 2 equals 0, and f of 4 equals 0. All right? Something else, though. And differentiable from 2 to 4. How do we know if it's differentiable from 2 to 4? You said earlier, how do we know if something's differentiable if the what's... We said looking at it, we know it's not any sharp turns.
The derivative doesn't change.
Derivative is continuous, okay? Is this derivative continuous? Well, let's think. Fractions, square roots, piecewise, special, so yes, okay? And f is differentiable from 2 to 4. Then, by Rolle's theorem, there must exist a number between 2 and 4 such that f prime at that number equals 0. So Rolle's tells us there has to be one, and we found it. Now, you probably say, I don't understand very much of what we just wrote down. That is quite all right. Continue. Here's what I would recommend that you do right now, okay? Keep this close by and use it as a blueprint for when you are asked to show that again, okay? You're just going to write down, since f is continuous on the interval and the endpoints are the same, and f is differentiable, then by Rolle's, blah, 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 blah. You're not going to change a whole lot in there, okay? So since you got an iPad, you can circle it, copy it, boom, go to the next one, paste it, change a few numbers, you're in good shape. Change the color, it looks like you wrote it all again. So, now don't pass it over to your next buddy, because if Ford passes his work to Sally, I'm going to know that Sally's handwriting is not the same as Ford, okay? So don't use that, all right? People have tried that before, but it doesn't work very well, okay? I was born at night, but not last night. Okay, so that's how you show that, okay? We've proved it down here, and we've found it right here. Okay? Let's look at another problem. Find all values on the interval -3 to 3 such that f prime of c equals 0. Well, do we know that there are any, first of all? Do we know that there has to be any? Because, I mean, let's be lazy for a second, okay? There might not be any. Do you know there has to be any between -3 and 3? How can you figure that out? Well, is the function continuous? Just looking at it. Is the function differentiable? Okay. If we put -3 in there, or 3 in there, are we going to get the same number out? Because we're going to do -3 to the 4th power or 3 to the 4th power. Either one of them is going to be the same number. Same thing to squared. So it looks like Rolle's theorem applies. So then, okay, it's safe to go ahead and move forward. So how are we going to solve this problem? To find the values. How are we going to find the problem? Come on, it is that simple. What do we do to find the values?
Just like set the derivative.
That's right. If there's any doubt, find the derivative, set it equal to 0. Not 9x, 6x. 4x cubed minus 6x equals 0. So how many answers do I expect to get? 3, okay? So keep on keeping on. See if you can figure out what my answers are there. Let's do that. Are all three numbers between -3 and 3? Very good. Yes, they are. Because 3/2 is about 1.5, and the square root of that's going to be less than that. So we've got our three answers now. How do I know that I was asked to find the x's and not the y's? I am asking for the x's. What in the question says we're looking for x's and not y's? Or maybe a different question. Go ahead. Find all values of c. Okay, there's only x's. But how do we know we don't need to take these and plug them back in to figure out up here? It'd be a pain in the rear to do that with those square roots, first of all. So we really hope that's not the answer. What would the question have had to ask if I wanted you to take these numbers and plug them in back up there? Anybody got an idea? Maybe we would have said, what is the function value at every place where the f prime of c equals 0? So just something to think about. I always want you to be thinking, because what are we asking for? Be sure you're answering the question that is asked. Okay? Questions about this. So what did we do? Found the derivative, set it equal to 0, solved. That's all we did. Okay, given f of x is this function, find all values of c on the open interval such that, blah. Do you think this is Rolle's theorem? This is MVT. Looking at it, hopefully it clues you that it's MVT because we gave it to you as a fraction here, okay? Can you solve that? Do you know what to do with that now? What are we asked to do? Right. We're going to put 4 in here. On the right side, we're going to put 4 in and get 5 minus 1. We're going to get 4 out. Minus, we're going to put 1 in, and we're going to get 5 minus 4, which is 1 out, over 4 minus 1. Well, we didn't do anything over on the left side yet. 4 minus 1 over 4 minus 1 is the number 1. So we're supposed to find out where the derivative equals 1. So how are we going to do this? Find the derivative, set it equal to 1 this time. How do we find the derivative of 5 minus 4 over x, if that's our function? Derivative of 5 is 0. How do we take the derivative of minus 4 over x? What are you going to do for that? Product rule, quotient rule, power rule? Power rule. Bring the x up and make this 4x to the negative 1. So now negative 1 times negative 4 makes it a 4x to the negative 2. So we're setting 4x to the negative 2 equals to 1. So what do we need to do to solve that equation there? 4x to the negative 2 equals 1. What would you do next? Anyone? Okay. That's one way of thinking of it. If I multiply this side by x squared and this side by x squared, it cancels with that, so I get 4 equals x squared. So x equals plus or minus dos. Okay? Have we done anything hard mathematically? Take the derivative, set it equal to 0. We haven't even given you hard derivatives to do. Most of these you're going to find we're not giving you hard derivatives to do. So what have we learned today? Rolles and MVT. Both of them, they're continuous. Both of them, they're differentiable. One of them, Rolles, the endpoints are the same. MVT, the endpoints are different. What's the big thing for you to remember when you're solving these problems? Find the derivative, set it equal to 0. Or find the derivative, set it equal to the slope between them there. I don't think it's hard stuff. Try not to get bogged down too much in trying to commit these to memory yet. They're going to fill in with you very well over the next few months. Okay. You've got plenty of stuff to work on. I'm not going to lecture on Friday.